might actually be very small. On the left-hand side, you have the current account balance deviation from the cross-country mean, which is very nervous. So you shouldn't be surprised if you don't get any significant coefficient for variables that matter, right? So because demographic variables, there's a lot of heterogeneity across countries, but there's not a lot of heterogeneity within countries across time. That's the problem. So the fixed effect, using the fixed effects estimator comes at a cost. Now, just another thing, you might want to put in time fixed effects in a regression, because these time fixed effects, they allow you to capture things that are time period specific, but the same for all countries. I mean, we're currently experiencing something that basically affects the entire world, right? The American government's infatuation with tariffs, right? So later on, when we look back at the year 2025, there is certainly a time fixed effect, basically something that affects all countries in the world, right? So we have worldwide growth spurts, we have worldwide recessions. In the wage equation, when you have a panel data set on wages, there might be periods in which all wages go up. And you cannot blame it on the individual or assign it to the individual. It's just something that happens to the entire economy. So XT, this guy is called XI, or the Americans would call it Xi. T, it's a time dummy. Then here's a thing that looks pretty dumb. Basically, you're computing the averages, and then you reverse averages and averages, and then you're back at square one, because you are basically you're computing these averages, and then you're just regressing these averages on averages. You're back in the cross-sectional dimension. And of course, the unobserved effect is back in. Now, why should you do that? Well, the reason is sometimes you have a dependent variable that reacts to the regressor, but maybe with a lag. It takes some time for the effect to unfold. Now, a smart way to model this is to spell out the dynamics, right? Run an ARMA model. Now, if you don't know what the dynamics are, and these dynamic models are sometimes, I mean, it's interesting, but what do you do with the fact that, whatever, the variable has a positive effect at lag 2, but a negative effect at lag 4, and at lag 5, it has a positive effect again. What do you do with that information? Now, a very simple, almost childish approach, but is that you do not use the original data, you use averages across some years, right? So I have several papers where I transformed the data into 5-year averages. Because I said, look, I know that the left-hand side variable reacts to the right-hand side variable. I know that the effect might not materialize immediately in the same period. I'm kind of hesitating to spell out a dynamic model, so I just have these, these large chunks that are regress on each other. So that's one way to justify that. Now, when you did microeconometrics, then the name of the game is not the fixed effects estimator, it's the first difference estimator. And in fact, the first difference estimator is a very simple thing, right? Now let me add that. If you have, this is beta xi1 I t minus 1 plus ci plus epsilon I t minus 1. If you subtract this from that, transforming data into differences, then the ci cancels out as well. So now, this is something that you may know from microeconometrics, like the difference estimator, of course, the difference in difference estimator. And this is how medical tests usually work, right? You have one group that gets a treatment, and then you observe what happens to these people, and then you compare the behavior of these people to the behavior of other people who are the control group. So you have differences because you observe 2 time periods, and you have different groups. So the nice thing about the difference estimator is it's very easy to compute. So if you are in the desert, right, and you don't have a sophisticated econometrics package, then maybe the first difference estimator is easier to implement. The bad thing is it throws away one observation, right? You're transforming 2 observations per unit into 1. Now, finally, as I said yesterday, in the same way that absolute purchasing power parity has a soft cousin in terms of relative purchasing power parity, the fixed effects estimator, which is a very powerful thing, has a soft cousin which is called the random effects estimator. And the random effects estimator is a generalized least squares estimator which uses the information about the structure of error terms to estimate more efficiently. But it's biased if the so-called, if this estimation is, if this assumption is violated. So this is so-called the random effects assumption. And the random effects assumption is that none of the regressors is correlated in any way with the error term, with the unobserved effect. So what is the beauty about random effects? The random effects estimator is efficient, but it's potentially biased. The fixed estimator is not so efficient, but eliminates the bias. So also random effects allows for time invariant regressors. So if you are interested in the effect of being an African country on economic growth, then of course you don't want to use the fixed effects estimator because that doesn't work. But the problem is the random effects estimator is biased if the random effects assumption is violated. So if this is different from, so the random effects assumption, the random effects assumption is that this is 0. If it's violated, then you get biased estimates. So it's a tough choice, right? You want to do random effects, but in many cases you're not allowed. So how do you know? Well, that's the last thing I want to show you. There's a gentleman called Jerry Hausman who did a lot of tests. And the Hausman tests usually work as follows. You have 2 estimators. One of them is efficient. That would be the random effects estimator, but potentially biased. And then you estimate the model using the one estimator, you estimate the model using the other estimator. Then you compare the 2 things. And this is, of course, the key thing. This is the so-called Hausman matrix, which is a complicated term with whatever of all kinds of things. Now, this is a 1 times k vector. This is the k times k matrix. This is a k times 1 vector. By the end of the day, you get 1 number, the test statistics, which is following a chi-squared distribution. So that's how we do it, right? And we have, and under the null hypothesis is that the random effect assumption is satisfied. These 2 guys should be very close. Now, please note that this is not a single number. It's 2 vectors. So this makes the whole thing so complicated, right? But under the null, these 2 things should be very close. So if you get a very small Hausman test statistic, then you cannot reject the random effects assumption. If you give you a very high number, that indicates that in fact this quadratic form is you're very far out, and then you have to reject the random effects assumption. That's what I wanted to tell you about panel data econometrics, right? And there's something about dynamic panel data estimation which I will not cover, and that's some literature. So, okay. Now, all this was done not to turn you into fully fledged panel data econometricians, but because it's very important that you see what we're doing in this exercise, right? And random effects and knowing kind of fixed effects, what is the benefit of running fixed effects regressions? What is the alternative? Random effects. How do you know whether you're allowed to do random effects? That's, I think, a very useful knowledge in all professions. Okay, so let me go back to the problem set. And let me guide you through the final thing. So let me show you the last thing, and today I brought my mouse, so it's much less stressful. This is the data set that I used yesterday. So here you see that, I mean, the fixed effects regression omits the regional dummies and the fixed effects, I tell Stata to do fixed effects by including this, this FE at the end. We haven't done a lot of, fancy things about the error terms, which we could do. But let's now, just to show you how to do a Hausmann test in Stata. That's so to test whether we have to, this is what I'm talking about. To test whether we have to reject the random effects assumption, we perform a Hausmann test, which generally compares an estimator that is consistent. I mean, I'm using biased or unbiased and consistent as synonyms. It's not quite the same, right? Forgive me, right? Biased is that the expected value of the estimator is the true population coefficient. Consistency means that if the sample increases, then you're converging to the true estimator, right? Anyway, that's just let me just confess that I'm aware of this. By the end of the day, it's about the wrong estimator that you get. Okay, so that is consistent with an estimator that is efficient but inconsistent if the underlying assumption, no correlation between regress and random effect, is violated. We perform the following steps. Now, estimate the fixed effects model without regional dummies. So that's what we do first. Right? Boom. That's the thing that we did, but we didn't have the regional dummies in there. The next thing is store this. So, and as we store it and give it a name, namely fixed. The next thing is we estimate the same model using random effects. Please note we don't have FE, but RE. There you go. And the last thing is Hausmann fixed, right? Now, Stata has stored the results from the random effects estimation, and now it does the Hausmann test. Now, what does this result tell us? The null hypothesis is that the random effects assumption is valid. Do you reject this null, or do you not reject it? Now, how do these tests work? And this is I'm making such a fuss about that because this is the very general thing, right? Right.
Yeah, so which means in this case, you should have used the fixed effect.
Yes. So the bottom line is we had this Hausmann test statistics, which is 39.86, which is very large. I mean, I don't know the chi-square distribution by heart, but I mean, the nice thing is that Stata gives me a p-value, and the p-value gives you the probability of a type 2 error, which is rejecting. The type 2 error is you reject something although it's correct. Now, the probability of committing such an error when you reject the null hypothesis is 0.0000. So bottom line is, right, if you think the chi-square distribution is skewed to the right. Right? And you're getting something that is way out there. So under the null, it could still be that such a Hausmann test statistic materializes, although the null hypothesis is correct, but it's very unlikely. And that's the point. The point is, conversely, if you reject the null hypothesis, the probability of committing an error is very low. So bottom line is, you can reject the random effects assumption, which means that using random effects is not a good idea. To be very frank, in cross-country panels, I never had the Hausmann. I always had to reject the Hausmann assumption, because the Hausmann assumption, I mean, these panels are, you have these cross-country panels, and they're so heterogeneous. You have so much unobserved heterogeneity that, and it's, you know, Vietnam versus Germany. I mean, which dimensions do these countries differ? You can, of course, have a lot of stuff that you can put into the regression. That's why we have multiple regression. But there's so many things in which our countries are different that, you know, it's just impossible to capture everything. And this wouldn't be an issue if the unobserved heterogeneity wasn't correlated with the variables that we have in the regression, but in most cases they are. And so in most cases we get, when we run a Hausmann test, we get this result, right? So what does that say? Well, it says that if it's really about estimating the most reliable coefficients, the most reliable set of coefficients, probably running this regression is the best idea. Now let me go back to Stata and let me you see that some of these variables have still survived. Actually, surprisingly many. Especially the prime savers share is still significant, which is something I wouldn't have expected in a fixed effects regression, because the prime savers share is not changing very strongly over time. But still, it's sufficiently strong to give the whole thing a bite. Now let's do the last thing, and that's the full EBA regression. Now, the IMF is kind enough to provide you with a do file. So you go here in Stata and you open the do file. I got a colleague in mind who's terribly afraid of doing this kind of thing. He says, never show students the structure of your hard drive. I don't care. I mean, okay, here's the do file. This is in fact, this is what you get from the IMF, right? This is the do file. And the first thing that you have to do is you have to choose file location. So there's a very clumsy way how I do it. I go back to the Explorer. This is called properties, in Germany Eigenschaft, and I copy and paste that thing into the do file. Right? Why is that? Well, because the do file wants to know where to find the data. And the do file also wants to know where to put the results. And now, this is a lot of stuff. Now, let me just tell you what it does. The first thing is to import Excel, right? So you can write that into a do file. First row sheet is basically, so it's a CA data set, and first row means the first row is data names. Sort IFS code year. XT set is important when you run panel data regressions, because not EView, Stata has to know which is the cross-sectional variable, which is the time series variable. And then it defines global cyclical, global fundamentals, and global policy variables. It's basically, and then the key thing to see is this. This is the regression. Now this is the regression. All the other things are post-estimation commands about, what should the tables look like. Now this is a specific estimator, which is a so-called Praise-Winston estimator. A Praise-Winston estimator is a GLS estimator that allows you to be very specific on the cross-country and time correlation of errors. And coming back to this issue here, you might make very different assumptions on how these errors are correlated across countries, whether we have heteroscedasticity, how they are correlated over time. And the Praise-Winston estimator allows you to put this into the regression and estimate more efficiently. So you read that the following, you have this estimator, right? I mean, if you want to learn more about this estimator, you just type help XDP-CSE, and then you get information. That's the beauty of Stata. This is the dependent variable. These are sets of determinants, and these have been defined up there. If these countries are in the sample, so you can define samples and subsamples. If years are greater than 1985 and smaller than 2020. And now here, what the IMF people say, you allow for an autocorrelation of error terms of the AR1 type. You could be much more general here. You could type in AR2 or whatever, but they use AR1. And heteroscedasticity, where you assume that for the first country, you have a variance of the error term. You have for the second country, and it differs across countries, but it doesn't differ across peers. Row type t-score is the way how to estimate this. And now, if all goes well, we just run this thing, and I hope this is the big thing here. Wait a minute. I do have to do one thing. Okay. So, let me run this thing, and let me hope that I will not get an error message, because otherwise I'll be, nope, end of do file. It's always a good, it's always good, right? So now what did we have? We have this, and ta-da! This is exactly the coefficients that the IMF estimate presents in its publication. So let me show you, right, on page 10. Right, you had the output gap minus 0.297. The commodity terms of trade interact with trade openness 0.291. And if you go to that thing, you get the same coefficients and also the same asterisks. The only thing which is a pain in the neck is that those variables have these odd names, right? And so we were kind enough to make your life easier. We have this EBA-CA modified do, and just to open that, right? This is something that you can do, labeling variables, right? You label variables, and then when you run that regression, then the labels appear in the output table, right? So that's very convenient. And of course, how you put that stuff into an Excel file, it's the outrag command. Outrag is super useful, right? Outrag using, and then you have, so you can, if you want to play with that, you can use the modified version. Now let me come to my last question. You may have realized that this is not a fixed effects regression. So the IMF runs something that's pretty sophisticated. Well, in fact, Michael Binder would say it's not. But still, it's kind of it's not ordinary least squares, it's generalized least squares. It has this, Price-Winston thing in it, but it doesn't have fixed effects. Now, 10 minutes ago, we have found that fixed effects is something that we probably should include. Now, the question is, why doesn't the IMF include fixed effects in that regression? And this is not an econometric question, it's a conceptual question.
They try to identify the individual specific of each country.
Mm-hmm. Heading in the right direction. Now, what is the goal of the whole thing? The goal is to arrive at a normative assessment of current account balances. So you want to, by the end of the day, what you want to do is you want to say, Greece's current account deficit is too high, Germany's current account surplus is too high, the British current account balance is just right. Now, when you include fixed effects, right, you're doing the following thing. You say, this country, suppose this is the current account balance and this is something else. You have a country-specific intercept which says the Greek government deficit prior to 2011 was very high. Why? Well, because Greece is Greece. And the German current account surplus is high. Why? Well, because Germany is Germany. So you're introducing, this is the power of fixed effects, but when you're planning to do what the IMF wants to do, you should not include fixed effects because it sucks up stuff that and it sweeps it into the fixed effect that you want to normatively assess, right? You don't want to have say, look, you have a high current accounts deficit. Is that okay? And you say yes, because we're just the way to have a high current account deficit. And you go to Germans and say, we think your current account surplus is too high. And the Germans say, we just love to save, and that's the way it is, right? And that's exactly what a fixed effect does. The fixed effect summarizes everything that's heterogeneous across countries without any possibility to assess that normatively. So you can no longer say your current account surplus is too high or your current account deficit is too high, because it would be, because of the fixed effect, takes this out of your hand. And so the IMF people are not to know the problem, and they actually address it in their explanation, and they say, given what we're planning to do, including fixed effects would not be the right thing to do. So we accept the possibility that we have these biased estimates, because anything we could do to eliminate that would be, destroy the entire project. So I find that a very nice lesson in that econometrics is not pure technical stuff, right? The way you estimate an equation sometimes depends on what you want to actually do. So if your goal is to have the most reliable estimates of these coefficients, and that's your goal, right? Then of course, fixed effects estimation is the name of the game. That's what you should do. But if your goal is to do that normative assessment of countries' current account balances, then including fixed effects is like, you at the very start you make yourself unable to do that. And so that's kind of the philosophy underlying that whole thing. Good. Okay. So so let me just the last thing I want to do is run that regression, right? Just file location, paste, then clear all, and then we run this regression, kind of the modified thing. I hope it's going to work as well. Now when you go here's a lot of regressions, right?